Welcome back to the deep dive. So today we are undertaking, a truly massive task.
We really are.
We are immersing ourselves in the comprehensive mathematics of the unified coherence theory, specifically the geometric foundations treatise. And, this work isn't just an incremental step. It's framed as a generalization of one of the greatest geometric achievements of the last century.
That's absolutely right. Our mission today, really, for you listening, is to unpack the rigorous analytic core of this geometric program. Think back to Grisha Perelman's triumph with Ricci flow.
Right, that was monumental.
Exactly. That flow smooths geometry, resolves singularities, and, ultimately proved the Poincaré conjecture. The UCT, developed by Philip Lillian, takes that foundational framework and dramatically extends it. And it does this by doing something crucial: introducing torsion.
Torsion.
Okay, and establishing a series of profound new conservation laws that govern geometric evolution. It's quite ambitious.
So the conceptual leap here is huge then. We're moving beyond just the curvature of space, how it bends, to include its twist and spin. The central concept we are dissecting is the coherence flow, an evolution equation for geometry that the paper suggests is capable of unifying geometric principles with concepts, traditionally reserved for thermodynamics and even quantum mechanics. It's positioned as, the fundamental geometric engine driving the universe.
Yeah, that's the claim. And by the end of this deep dive, you will grasp the rigorous mathematical architecture, the theorems, the specific derivative estimates, the crucial dual invariants, all the things that underpin this theory of total coherence information conservation.
So we're getting into the weeds of the math.
Absolutely. This is pure mathematics, partial differential equation analysis, really applied to fundamental physics. We need to understand the analytical heavy lifting required to make this new torsion-augmented theory, viable.
Okay, let's start at the beginning then. If we're defining a new geometric flow, we need sort of a stage and a cast of characters. What is the fundamental geometric setting UCT relies on? And what distinguishes it from standard Riemannian geometry?
Okay. The stage is set on a smooth, closed three-manifold. That's a pretty common starting point in modern geometry, nothing too unusual there.
Right.
But the real difference, the conceptual break, lies in the connection used. Standard general relativity uses the Levi-Civita connection.
Which assumes no torsion, right? Symmetry.
Exactly. It assumes the underlying space is symmetric, torsion-free. UCT, however, requires a Riemann-Cartan connection.
Okay, and why is that specific choice of connection so pivotal? Why Riemann-Cartan?
Because the Riemann-Cartan connection essentially, by definition, induces a non-zero torsion tensor. It allows the geometry to twist, not just curve. And Lillian's central assertion, really the core bet, is that torsion isn't just some mathematical curiosity or, an unnecessary degree of freedom. It's argued to be a fundamental component of the evolving geometry that must be conserved. The entire analytic program hinges on accepting that twist or chirality as real.
This sounds conceptually similar, in a way, to how matter and gravity are coupled. Is there, a coupling parameter involved in managing this interaction between curvature and torsion?
Absolutely, there is. The system involves a coupling constant, typically denoted alpha, which governs the strength of the interaction between the curvature and this newly introduced torsion field.
Okay.
And this leads us to the two geometric objects that evolve over time under this coherence flow. First, you have the symmetric positive definite tensor, math-Kelly zone. Think of this as representing the evolution of the geometry itself, the metric, the shape of space, how distances are measured.
Got it. Standard geometric evolution, in a sense. And the new kid on the block.
That would be the antisymmetric torsion chirality field. Omega, this is the quantity that explicitly captures the torsion, the intrinsic chirality embedded within the geometry.
So we have the familiar evolution of shape, but now it's intrinsically linked, coupled, to the evolution of spin or twist, omega oj.
Precisely. It's a coupled system.
This dual evolution brings us then right to the heart of the theory. The coherence flow equation. It's labeled as equation 1.1 in the source material. Can you lay out the central partial differential equation for us?
Sure. The coherence flow is defined by the rate of change of the geometry. It looks like this. Partial math-Kelly 2 plus omega oj.
Okay, let's break that down structurally, because just reciting the symbols isn't always enough, right?
Yeah.
The left side, partial math-Kelly, that's the change in geometry over time. Simple enough. The right side tells us what forces are driving that change.
Precisely. The time evolution of the geometry is dictated by those two terms inside the parentheses, scaled by μ/2. math-Kelly is the familiar Ricci curvature tensor.
The one from standard Ricci flow.
Exactly. That's the component that drives the geometry to smooth itself out, just like in Perelman's original work. The critical distinguishing feature, the UCT addition, is the inclusion of that second term, omega, torsion chirality field.
So the geometry is evolving not just to minimize curvature, but it's also responding dynamically to its own intrinsic twist. Is that the idea?
Yes, exactly. And the paper rigorously confirms this is a true generalization. Analytically, if you were to impose the condition that omega I must be identically zero,
Then the equation just simplifies.
it immediately reverts to the standard Ricci flow equation, partial mathematical area. So this shows UCT is built to contain all the prior successes of Perelman's program while extending it into this new regime where torsion is active and, crucially, dynamic.
Okay. Now, regarding the axiomatic structure, the text notes the evolution happens over a multi-vector time parameter, $2. But then it says they must reduce this to a scalar parameter to achieve what mathematicians call parabolicity. This sounds like a necessary mathematical simplification, maybe? Why is that specific property parabolicity so vital for actually solving this PDE?
Oh, it's absolutely vital. And it's one of the first major analytic hurdles you encounter with these kinds of flows. Parabolicity is the property that ensures the PDE behaves mathematically like, say, a heat equation or a diffusion equation.
Okay, like smoothing things out.
Exactly. Think about how heat flows. It starts localized and it spreads out, smoothing temperature gradients over time. That is a well-behaved, stable process. A parabolic PDE inherently describes that kind of smoothing process.
So without forcing it into parabolicity, what happens?
Well, without reducing the multivector time to a scalar, the equation would likely be hyperbolic or possibly even more complicated. Hyperbolic equations, like the wave equation, propagate disturbances without smoothing them, and they often require much more complex initial and boundary conditions. They can lead to solutions that form shocks, blow up instantly, or are potentially chaotic and non-unique.
Not good if you want predictability.
Not good at all. So by forcing it into the parabolic class through this temporal reduction, they ensure the resulting equation has a built-in smoothing dissipative effect. This makes it mathematically tractable, solvable, and stable, at least over short time intervals. It basically allows the heavy machinery of PDE analysis to get a foothold.
Makes sense. Before we move on from the setup, what is this coherently closed manifold definition the paper gives?
Right. A manifold is defined as coherently closed if its Ricci curvature is 0, and it is simply connected, meaning no holes or handles, topologically simple. This sets the ideal static state in UCT. It's sort of the geometric vacuum state, perfectly smooth in terms of curvature, yet potentially containing the dynamics related to coherence and torsion.
Okay, so we have the equation. Now comes the really hard part, I imagine, proving the equation actually works, that its solutions are stable, well-behaved, unique. This section, proving mathematical existence and stability, sounds like the dense core of the mathematics focus. Let's tackle Theorem 3.1, short-time existence and uniqueness.
This really is the bedrock. You have to start here. The theorem guarantees that if you start with a reasonable initial geometry, what mathematicians call nice initial data, a smooth, positive, definite metric math-cal-C with bounded initial curvature and bounded initial torsion, then the coherence flow solution is guaranteed to exist and be unique for a certain finite time interval, say, same inner and happening.
And why is that so fundamental?
Well, if we couldn't prove this, the entire UCT would be pure speculation. The equation might not even have solutions, or the geometry could simply vanish or tear itself apart immediately. This theorem provides the first rigorous assurance that the flow is well-defined, at least initially.
And central to this proof is that mathematical trick we touched on earlier, the DeTurck modification. If the original coherence flow equation is so difficult, how does this modification make it solvable? What's the cost of using this technique?
Right, the DeTurck modification. It's a classic technique, actually, used quite often to simplify nonlinear geometric flows, including standard Ricci flow. The original flow equation is complicated partly because of its inherent freedom of movement, what's called diffeomorphism invariance. You can choose coordinates in infinitely many ways.
Which makes the nonlinear terms hard to pin down.
Exactly. It makes controlling those nonlinear terms incredibly difficult. The DeTurck trick introduces an extra term into the flow equation. This term doesn't change the underlying geometry of the solution, but it effectively fixes a reference coordinate system, acting like a gauge fix.
Like putting in a temporary anchor, essentially.
Yeah, that's a good way to think about it. By applying this modification, they successfully transform the nonlinear PDE into one that is strictly parabolic. This is crucial because it allows the use of standard, powerful PDE techniques like methods based on fixed-point theorems to rigorously prove that a solution must exist and that there's only one solution coming from those specific initial conditions.
Okay, but what's the price? Is there a downside?
The price, if you want to call it that, is a slight loss of pure geometric interpretation during the calculation itself. The modified equation isn't purely driven by geometry alone because of that extra term. So after proving existence for the modified flow, you have to perform an extra step to show that the solution you found actually corresponds to a solution of the original coherence flow equation, just perhaps at evolving coordinates. You have to carefully account for the gauge fix to ensure the result is genuinely geometric.
Makes sense. Now, a key part of the stability proof involves controlling the metric itself. They have to guarantee that the evolving tensor, math-cal-scary, remains positive definite throughout the flow. You mentioned this is done by bounding the eigenvalues, usually called lambda and mood. What's the geometric disaster they're trying to prevent here?
They're preventing geometric collapse or degeneracy. Remember, math-cal-ci is the metric tensor. It defines distances. If its eigenvalues were allowed to approach zero, it means distances are shrinking infinitely fast in certain directions.
So space itself would sort of flatten out or pinch off?
Exactly. The geometry would essentially collapse into a lower dimensional object. Like, imagine a 3D ball suddenly collapsing into a flat disk, or even a line. That would be a singularity, a breakdown of the manifold structure. The estimates ensure this doesn't happen, at least during the short time the theorem guarantees existence.
And specifically, the analysis provides this detailed estimate on the rate of change of the eigenvalues. Partial lambda plus sub-omega lambda. Can you unpack that a bit?
Yeah, this is a powerful statement mathematically. It shows that the rate at which an eigenvalue lambda might try to decrease, making the geometry collapse, partial lambda becoming very negative, is bounded. It can't decrease faster than a rate proportional to the eigenvalue itself times the maximum initial curvature and the maximum initial torsion.
So as long as the starting curvature and torsion are finite.
The eigenvalues are guaranteed to remain strictly positive for that short time interval, d and d any. This guarantees that math-cal-ci remains a proper, non-degenerate metric tensor. It's the first critical guarantee that UCT's solutions preserve the very nature of space itself, its dimensionality.
Okay, so the geometry is safe from immediate collapse, but we still need to ensure its smoothness. Geometry can become rough, right? Develop singularities, which mathematically means derivatives are running off to infinity. This is where the famous Shi estimates come in.
Yes, the Shi estimates are absolutely crucial for controlling derivatives. They were foundational to Perelman's work on Ricci flow, and Lillian's UCT must extend them to accommodate this new torsion term, omega A. The goal is conceptually simple but technically very hard. Prove that if the manifold starts smooth, it remains smooth, preventing the formation of mathematical singularities. Think of infinitely sharp points or tears in the fabric of space during the evolution.
And the technical structure of the bound is quite illuminating. The first-order estimate shows the bound on the first derivative, the Navier-Bath-Colombo, depends on initial conditions, and, critically this time, dependence. What does that t to the minus 1/2 dependency tell us conceptually?
That T-Teldal term is really the signature of parabolic flow stability. It tells you how the flow handles initial roughness. It shows that the derivatives, how sharply the geometry can curve, are allowed to be very large right near the starting time, because the denominator is tiny then.
Okay.
But as time progresses, even a tiny bit, that T-Teldal term starts to decrease. It shows that the smoothness degrades slowly and predictably. It confirms that the smoothing effect inherent in parabolic equations is immediately at work, but it's fighting against the initial roughness in a controlled manner. It behaves very much like the inverse square root decay you see in a heat kernel spreading heat from an initial point source. Very characteristic.
And controlling higher derivatives must be exponentially more difficult, especially now with torsion complicating all the interactions.
Oh, absolutely. It is. The proof for the higher order estimates requires a deep inductive argument. They have to derive the evolution equation for higher derivatives, things like partial Sandok, and this involves incredibly complex nonlinear terms arising from the interplay of curvature, torsion, and multiple derivatives.
This is like a mathematical nightmare.
It's definitely where the real analytic grunt work is performed. They have to meticulously control all these interaction terms, often relying on sophisticated tools like Young's inequality to bound nasty cross terms, and ensure that the Laplacian term, like delta VK all in the outlines notation, dominates. It's the dominance of the Laplacian that maintains the desired parabolic smoothing behavior for all derivatives, keeping the solution smooth.
Okay. Now, since UCT introduces torsion as an active field, not just a background structure, they must also prove that torsion itself doesn't destabilize the geometry. How is this torsion perturbation control achieved?
Right, this is a stability proof specific to UCT, something Perelman didn't need for standard Ricci flow. It essentially ensures that the newly introduced element, omega g, doesn't grow uncontrollably and wreck the whole system. The theorem states that if the initial torsion is small and bounded, say omega epsilon initially,
Then it stays small.
then it remains small and bounded, omega epsilon, during the short-time solution guaranteed by theorem 3.1.
In simple terms, you can't just add a new field to your equations and hope it behaves nicely. You have to prove its energy or its magnitude doesn't run away.
Exactly. If the torsion field were allowed to grow exponentially, for instance, it would quickly overwhelm the curvature terms, invalidate the bounds on the eigenvalues we just discussed, break the derivative control from the Shi estimates, and likely lead to an immediate geometric catastrophe. This stability proof shows that the coherence flow itself manages the torsion field internally, ensuring it evolves constructively alongside the metric rather than destructively against it, at least for small initial torsion.
Okay. Finally, in this section on stability, we arrive at the non-collapse condition. This is a key legacy from Ricci flow analysis. We need some guarantee that the manifold retains its dimensionality and structure over time, right? Theorem 5.1 is called kappa non-collapse plus carry.
Yes, this condition, which generalizes Perelman's original reduced volume condition, is vital, especially if you want to think about the long-term predictive power of the flow beyond just short-time existence. Geometrically, a non-collapsing condition means that for any reasonably sized ball within the manifold, its volume does not shrink away to zero too quickly as the flow evolves.
It doesn't just vanish into nothing.
Right. Specifically, the condition usually involves looking at the volume of balls at a certain scale. Perelman's condition, which this extends, says that the volume die must be bounded below by something like kappa tau, where kappa is some positive constant. This ensures the space maintains a certain voluminous quality at small scales.
Can you give us a strong analogy here? What does geometric non-collapse look like, maybe compared to what collapse would look like?
Okay, imagine the manifold is like a big, complex piece of infinitely stretchy dough. The coherence flow is kneading this dough, evolving its geometry. Non-collapse ensures that as you knead it, you can never squeeze any portion of it so tightly that a significant chunk of it shrinks down to effectively become a thread, 1D or a 0.0D, almost instantly.
So it keeps its 3D structure locally.
Exactly. Collapse would be the dough suddenly tearing or being compressed to essentially zero volume in some region, reducing its effective dimension. The kappa non-collapse plus condition in UCT guarantees this kind of geometric stability. The structure remains robustly three-dimensional, rich enough to support the physics proposed by the theory, even as the flow works to smooth out curvature and manage torsion. It prevents the manifold from degenerating into lower dimensions.
All right, so the flow's existence and stability, at least for short times, are proven.
Yeah.
Now, we seem to pivot from the sort of geometric mechanics to energetics and information. This is where UCT defines the character of its evolution using these dual invariance functionals that track the total state of the system.
That's right. These dual functionals are not local quantities. They are integrated quantities defined over the entire manifold. You can think of them as mathematical thermometers or maybe barometers for the system, showing us the overall state and, crucially, the direction of evolution, the direction of time, in a sense, and how information or coherence is conserved.
Let's start with the first one, the coherence entropy functional, denoted mathcal SEC. How is it defined? And how does it explicitly generalize our usual ideas of thermodynamic entropy?
Okay, mathcal is defined by this integral. Mathcal plus nabla F2 plus beta omega to E fist dBt. Let's break that down. It incorporates the standard components you see in Perelman's entropy functional for Ricci flow, namely the Ricci scalar curvature, and a gradient term, nabla F2A2, related to a potential function $5.
Okay, those are familiar from Ricci flow.
Yes. The key addition and the specific generalization for UCT is that third term inside the integral, beta omega 2. This term is proportional to the squared magnitude, essentially the energy density of the torsion field omega.
So the torsion field itself is explicitly contributing to the system's total entropy budget. An increase in torsion can increase this geometric entropy.
Exactly. This inclusion means that the geometric dissipation normally associated with smoothing curvature and the dynamics of the torsion field are linked together into a single measure of informational disorder or entropy for the system. If torsion increases, all else being equal, this entropy measure, math-cal, increases. Metas is just another parameter here.
And its critical dual invariant, the counterpart, is the resonance functional. What aspect of the geometric state does this functional capture? It sounds like the opposite of entropy.
It's designed to be exactly that, the counterbalance. The resonance functional aims to capture the torsional coherence, the geometric order, or perhaps memory inherent in the spin structure of the geometry. Math-cal is defined by a slightly more complex integral. Math-cal 1, Math-cal 2 plus 3, 1.
Okay, that looks more complicated. Involves the scale parameter tau, but notice the conceptual difference.
Yes. Look inside the main parenthesis, where Math-cal added a term proportional to torsion energy, plus beta omega 2, suggesting torsion contributes to disorder. Math also subtracts the torsion term. Kappa is another coupling constant here, potentially different from beta or alpha. This immediate opposition in how they treat the torsion energy is what establishes the necessary mathematical duality for a conservation principle to emerge. One goes up with torsion, the other goes down.
Right, this duality brings us to the core of this section, proving monotonicity, which is detailed in Theorem 7.1. We discussed the need for predictability earlier, but why must the flow guarantee this kind of unidirectional evolution for these specific functionals?
Well, in physics, and especially in geometric flows that might model cosmology, monotonic invariants are crucial because they effectively define the arrow of time for the system. They tell you which way is forward. If the flow were not monotonic, if this entropy mathically could randomly increase and decrease, or if mathically bounced around unpredictably, the theory would be analytically unstable. It wouldn't have predictive power, making it useless for understanding cosmological evolution. We absolutely must prove that the geometric evolution described by the coherence flow has a definite directionality reflected in these functionals.
And the proof delivers this directionality, correct?
Yeah.
The coherence entropy, mathically is shown to be non-decreasing over time. So it's final time.
That's correct. This is essentially the mathematical derivation of the second law of thermodynamics, but applied directly to the geometry itself. Informational disorder, as measured by Math-Cal A, must generally increase or stay the same as the geometry evolves under the flow.
And simultaneously.
Simultaneously, they prove the opposite for the resonance functional. Math-Cal is shown to be non-increasing. So Hahn-Krocky Math-Cal is shown to be non-increasing. So as the universe evolves geometrically according to this flow, it sacrifices its torsional coherence, measured by Math-Cal, for the accumulation of entropy, measured by Math-Cal. Order decreases, disorder increases.
Now, proving this requires, as you said, serious mathematical heavy weaponry. We need to understand the role of something called the torsion-Bochner identity, mentioned as Lemma 4.1. In the context of proving monotonicity for these functionals, what does this identity actually do?
Okay, the torsion-Bochner identity is the mathematical rulebook, if you will, that precisely details how the new torsion field omega interferes with or couples into the existing geometric dynamics governed by curvature. The standard Bochner identity used in Ricci flow relates curvature terms to the Laplacian of gradient terms, like del Tyndall F22. When torsion is introduced via the Riemann-Cartan connection, this identity gets modified. It picks up additional cross terms that explicitly involve omega. The outline mentions one such crucial term, 2 omega phi nabl. This term shows torsion directly interacting with the gradient field 5-all.
So the identity essentially demonstrates mathematically exactly how the twist changes the way curvature gradients evolve and dissipate.
Precisely. It allows the mathematician, when calculating the time derivative of Math-Cal upstroll, to substitute these Bochner relations into the integrals. This clarifies how the torsion terms affect the evolution rates and allows for detailed estimates. Without this identity, trying to track how torsion influences the evolution of curvature and gradients would be an intractable mess. It is the core analytic mechanism that mathematically links the dynamics of the metric to the dynamics of the torsion, making the proofs of monotonicity possible.
And performing those detailed estimates, particularly for the decay of the resonance functional, leads to one of the most significant and maybe surprising constraints in the entire paper, the required bounds on that coupling parameter gamma.
Yes, this is where abstract PDE analysis potentially hits a concrete physical requirement. When they compute the time derivative of Math-Gamma using the torsion-Bochner identity and various estimates, they arrive at an inequality that looks something like fract. Some terms, including a crucial integral term like 1 meth gamma plus nabla 2f2 plus other potentially negative terms.
Okay, and for math to be non-increasing, that derivative needs to be less than or equal to 0.
Exactly. And that integral term involving the squared quantity Taller-1 is always non-negative. So for the whole expression frac to be guaranteed non-positive, meaning math is non-increasing, that coefficient multiplying the integral 1 gamma must be non-negative. Or, more strictly, they probably need it positive to ensure decay unless the system is in a soliton state.
Which mathematically mandates the constraint. Gamma must be less than 18 pounds. A gamma 18.8, that's a hard numerical constraint derived from the math, seemingly placed on a physical coupling constant of the universe, if this theory holds.
It is a phenomenal insight, assuming the derivation is correct. It tells you that the UCT framework isn't arbitrary. It's highly sensitive to its internal parameters. If the actual physical constant gamma, which governs how strongly torsion contributes to this resonance measure, were ever found experimentally to be equal to 18 AEIs or greater, then the entire coherence conservation framework described here would mathematically fail.
Why? What would break?
The resonance functional math fallacy would cease to be a reliably decaying invariant. Its derivative could become positive under some conditions. The guaranteed monotonicity, the geometric arrow of time associated with math decay, would collapse mathematically.
Wow. I see this as the theory really putting its money where its mouth is, mathematically speaking. It's not enough to just define the equation and the functionals. The internal consistency of the mathematics dictates that the universe itself must adhere to this rather narrow window of coupling strength for the resulting theory of information conservation to be analytically sound.
Exactly right. It's a required numerical condition derived purely from the pursuit of mathematical consistency and predictive stability within the geometric flow itself. Quite remarkable.
Okay, so we've established this picture. Rising entropy and decaying resonance, both rigorously proven through things like the torsion-Bachner identity and specialized estimates, and crucially dependent on that gamma 18.1 constraint. Now we arrive at what sounds like the core theoretical breakthrough, the coherence entropy equivalence principle, stated as theorem 8.1.
Yes, this is presented as the central conservation law of the UCT. It starts by defining the total coherence energy, let's call it EC, simply as the sum of the entropy functional and the resonance functional we just discussed. C plus EC.
Okay, just adding them together.
Exactly. And the theorem then states that this total energy, this combined measure, is conserved throughout the evolution under the coherence flow. Mathematically, FrafCol plus C plus dollars. The rate of change of the total coherence energy is 0. It's constant over time.
Which means the geometric evolution, according to UCT, is not just a gradual winding down towards maximum entropy like simple heat death. It's a perpetual, perfectly balanced exchange.
It is the ultimate trade-off, and it's derived directly from the rigorous mathematics of those dual monotonicity proofs we just went through. Since frac and frac, the only way their sum can have a time derivative of exactly 0 is if the rate of entropy rise precisely equals the negative of the rate of resonance decay.
So any increase in entropy is exactly compensated by a decrease in resonance, and vice versa if the system were somehow driven backward, though the flow naturally goes one way.
Correct. In essence, the geometry evolves by dissipating curvature and generating entropy, which increases math-cas, while simultaneously using up or reducing its torsional resonance or order, which decreases math-cas. The balance is exact.
The profound insight here, then, is that the total coherence information, what you might think of as the geometric memory or complexity of the universe, is claimed to be constant. It's never truly lost. It just changes form, shifting between curvature-based disorder and torsion-based order.
That's the interpretation put forward. When you think about the fate of information in standard geometric theories, especially involving singularities like black holes, information loss is a huge problem. UCT proposes a mathematical mechanism baked into the geometric flow itself for information permanence, encoded as this constant balanced exchange between entropy and resonance.
Let's turn briefly to the special stationary solutions identified by the theory, the resonant solitons mentioned in section 10. What defines a soliton in this context?
Right. Resonant solitons are specific geometries that are stationary solutions to the coherence flow. They represent the fixed points of the system geometries that stop evolving because they have reached a state of perfect dynamic equilibrium.
They don't change anymore under the flow.
Exactly. And this equilibrium state for these solitons is defined by the condition math color omega dollars, or perhaps more generally, the combination driving the flow, math color plus omega doll, becomes related to just the metric itself in a specific way, like a gradient or a constant multiple, causing the flow to halt or proceed self-similarly. The simplest case might be when curvature and torsion structures are precisely balanced against each other.
And these stable, non-evolving, or self-similarly evolving geometries are categorized into three types.
Yes, the paper classifies them based on their symmetry properties. Isotropic, uniform in all directions, chiral, possessing a handedness, and helicoidal, having a screw-like structure, solitons. These solutions are key because they represent potential stable end states or configurations that geometry might settle into, sort of like the coherently closed state we mentioned earlier, but now extended to allow for scenarios with non-zero yet perfectly balanced curvature and torsion.
Okay. Now let's try to tie these rigorous mathematical principles, the
Yeah.
conservation law, the essential role of the omega term, the gamma constraint, to more tangible theoretical applications in physics. The outline mentions quantum decoherence. How might UCT model that?
Quantum decoherence, the process by which quantum systems lose their superposition and entanglement when interacting with an environment, is notoriously difficult to model from a fundamental geometric perspective. UCT offers a potential mechanism. It models decoherence as a process where the underlying geometry undergoes entropy gain, math scale increases, at the precise expense of resonance loss, math decreases.
So the loss of quantum coherence is interpreted geometrically.
Yes, it's interpreted as the geometry sacrificing its torsional order, resonance, to increase its overall disorder, entropy, driven by interaction. The math provides a functional justification, rooted in these conserved quantities, for why superposition might break down over time from a geometric viewpoint.
And the thermodynamic arrow of time. You mentioned the monotonicity gives it direction.
Right. It's potentially elevated from just a statistical concept, more likely states, to a fundamental geometric necessity. Since the monotonicity of entropy is mathematically mandated by the coherence flow equation, assuming gamma 18.1, UCT suggests that the perceived arrow of time is simply the global signature of the universe's geometry evolving along this flow, inevitably moving towards states of higher math color and lower math call. The observed direction of time could be fundamentally driven by the inherent dynamics, possibly a torsion bias within the geometry itself.
Okay, finally, let's address cosmic anisotropy. This seems counterintuitive. If total coherence is conserved globally, shouldn't the universe end up perfectly smooth and symmetrical? UCT suggests otherwise, allowing for residual anisotropy. How does that work?
This is an important distinction. The conservation law, Frath-Kalar-C, applies to the total integrated energy over the entire manifold. It does not mandate that the geometry must become perfectly uniform or isotropic locally.
Ah, so global conservation doesn't mean local uniformity.
Exactly. The theory mathematically allows for residual anisotropy to persist. This means that non-zero torsion, omega nodal, can exist locally, representing preferred directions or chirality, even within a globally coherent framework where the total math cal is constant. This local asymmetry, this omega nodal, can be thought of as the stored information, the memory of the flow's history, preserved in the torsional structure.
So the existence of observable small-scale non-uniformities, or perhaps even a slight overall chirality in the cosmos, what astronomers might call cosmic anisotropy, could potentially be explained within UCT. It wouldn't be a flaw, but a feature.
Potentially, yes. It provides a mechanism where the geometry preserves information, total coherence, by converting some of it into a persistent, non-symmetric torsion field, omega dollars, rather than forcing everything into a perfectly smooth, maximally symmetric, information-poor state. Furthermore, the paper notes that this total coherence energy is mathematically conserved even during radical geometric shifts, such as topological transitions, like wormholes forming or closing, hypothetically, suggesting a profound stability of this information measure across cosmic evolution.
Okay. As we wrap up the discussion on the analytic core established in this paper, let's look forward. Sections 11 and 12 outline remaining open problems for this massive theory. What are some of the big analytic hurdles still facing the researchers?
Well, the most significant one, mentioned earlier, is that the current work primarily establishes short-time existence and stability. The biggest remaining analytic challenge is proving the long-time behavior of the coherence flow.
What happens over cosmic timescales?
Exactly. Does the flow continue indefinitely, perhaps approaching one of those resonance solitons? Or if it does terminate in finite time, does it form singularities? And if so, can those singularities be understood and potentially resolved or continued through, similar to how Perelman developed techniques to handle Ricci flow singularities? This requires proving that the flow maintains control over its derivatives, like extending the Shi estimates, over potentially infinite time horizons. That's a huge undertaking.
And what other areas are flagged for future integration?
Several key areas. They need to establish the spectral gap for the relevant geometric operators. This is often a crucial requirement for quantizing the theory. Formalizing the quantum coupling mechanisms to properly link this geometric flow to quantum field theory is another major goal. Developing a rigorous thermodynamic temperature interpretation, moving beyond just the formal definition of entropy math LSI, is also critical for connecting to real physics. And the link to something called phase mathematics is mentioned, suggesting potential integration with geometric phases, Berry phases, and perhaps nonlinear wave dynamics.
And the most exciting foreshadowing, perhaps for us in the audience, concerns part 3 of this work.
Yes, the paper mentions that forthcoming work, Part 3, is expected to integrate the universal field tensor, which presumably aims to link this pure geometry to known physical forces like electromagnetism or gravity in a more unified way, and, perhaps most thrillingly, propose concrete experimental detection pathways.
So moving from math towards observation.
Exactly. This would potentially move the theory from the abstract mathematical constraints like gamma 18.8 towards identifying signatures that could, in principle, be searched for in cosmological data or lab experiments. That's the ultimate goal, of course. #outro. So if we step back and look at what we've covered today, what's really been established mathematically is that this proposed generalization of Ricci flow, the coherence flow, fundamentally tries to rewrite the rules of geometric evolution. It's suggesting it's no longer just about simple dissipation towards uniformity like standard heat flow. Instead, it's about a precise, mathematically constrained exchange and equivalence principle where curvature entropy and torsional resonance are constantly traded against each other, one for one.
And the mathematical journey to establish this was crucial, rigorously proving short-time existence using tools like the DeTurck modification, maintaining smoothness through extensions of the Shi estimates, controlling the new torsion term, ensuring non-collapse, and defining that precise trade-off via the torsion-Bachner identity and the resulting monotonicity proofs. All of that was necessary for the UCT to claim that total coherence information is conserved. This entire intricate mathematical structure rests fundamentally on the idea that the geometry's information isn't lost, but preserved through this delicate balancing act between these dual invariants, entropy and resonance.
And this mathematical architecture, remarkably, demonstrates how the universe could evolve, dissipate energy locally, increase entropy overall, and still potentially retain its memory and complex structure. It even predicts, as we discussed, the possible persistence of residual anisotropy places where the torsion field, omega-omega, remains non-zero, holding some of that conserved coherence. The analytic work presented here aims to transform what might have been just a conceptual possibility into a rigorous mathematical necessity, provided, of course, that those crucial coupling parameters like lemma fall within the analytically required bounds.
And this leaves us, perhaps, with the ultimate provocative thought, connecting all this abstract mathematics directly back to the observable world around us. If the entire geometric viability of UCT hinges on that physical constant gamma dual being strictly less than E10D, and if the theory predicts that some residual anisotropy, omega d any, must be present somewhere for coherence conservation to actually hold dynamically, then how might future experiments, perhaps those designed to precisely measure cosmic spin or background chirality or other subtle geometric effects, actually test this? Could they measure this predicted value of gamma? We've seen the rigorous mathematical proof today that demands this geometric balance. But the final ultimate test is whether the universe's true constants actually fit within the narrow, analytically determined bounds required by this ambitious and mathematically magnificent theory. Something to think about.